Hi there, it is Paul and Andrew here, and today we're going to teach you about string matching and the KMP Knut-Morris-Pratt algorithm in particular. The string matching algorithm is commonly used for tasks such as searching for words in big texts, DNA matching, plagiarism detection, and any other tasks which require pattern matching. There are several algorithms available for use to match strings. These are the naive method, the Knut-Morris-Pratt algorithm, the Boyer-Moore-Horspool algorithm, and by making use of finite state machines. The main difference between these algorithms is the approach they use in matching the strings and the time in which they finish the computation. Although it sounds complicated, we hope by the end of this lecture we will provide you with a better understanding of how to use the KMP algorithm to match the strings.
So, how does KMP work anyways? It pre-computes a table of prefixes which is calculated for the chosen substring before the beginning of the matching phase. The matching happens from left to right. Whenever a mismatch occurs, the prefix table is used in order to determine how far the substring can be shifted so we can avoid unnecessary comparisons. Because it uses the patterns computed in the prefix table, the algorithm is extremely efficient when applied to strings over very small alphabets where patterns are more likely. As the key of KMP is the prefix table, let's find out how it is generated. Starting from the left end of the word, we iterate through its letters and try to find the longest prefix that is also a proper suffix of our substring. Here, the substring is the string which starts at the first letter of the word and ends with the letter we are currently at. To understand it better, let's see an example of how this works. We'll use colors to represent our current position in a better way. Here, the blue color is the last known prefix, initially set to 0. The red color is used for the current letter of the iteration as well as for the letter we will be comparing it against. For the first letter, we set its prefix to 0 because there's no proper suffix with a length less than 1. Now, we go to the next letter, which is n, but our I is still 0, so we don't enter the while loop. Now we compare the letters highlighted in red, A and N. They are not the same, so now N prefix becomes the last value of I, which is still 0. In this iteration, I is still 0, but this time we find a match because A equals A. So we increment I, which is now 1. So A's prefix becomes 1. Now we move to the next letter, which is again N. I is no longer 0, but N equals N, so we still don't enter the loop. Therefore, we go forward and we get a match again, incrementing I as a result, which becomes 2. The prefix of N is therefore 2. We go through the same sequence for the next letter, which is A, and as a result, I will become 3 and so will the prefix for A. On this iteration, we find S. Now, we get that S is not equal to N, so we finally enter the loop. We move I's position to the value of the prefix of I's letter. S is not N, so we change I again. I is now 0, so we no longer enter the loop. S is not equal to A, so its prefix will be 0.
Now that we have completed our prefix table, we are ready to begin the matching stage of our algorithm. We start at the leftmost letter of the text, the N word P. The colors are used in the same way as for the prefix table. Red is characters which are currently in comparison, J and I plus 1, and blue is the current position in the substring we're trying to match. So let's start. We compare X with A. It is not a match, so we stay in the same position in the substring and go to the next letter in the text by increasing J. Next, A equals A. It's a match, so we go to the next position in the substring by increasing I and advance in the text as well. Next, B is not equal to N. We go back into substring, the position indicated by the current value of the prefix table. You can check the table on the right side of the slide. I is now 0. We get out of the loop, and because A is not equal to B, we only advance our position in the text. Next, A equals A. Both counters are increased. We again find a match in N equals N, so both counters incremented again. This happens again for the next iterations until we get to comparing N with S. This clearly doesn't match, and so we use the prefix table in order to see how far back we need to go in the substring. Turns out this is the third position in the substring, so I gets the value 3. We can now start the matching again without needing to go back to the beginning of the substring. This is the moment we see how the prefix table spares us of having to make useless comparisons, only to get the same result. Next, we go through the string again. n equals n. Increase both current positions in substring and text. A equals A. Again, advance in position. We then find a mismatch. S is not equal to n. Good guy prefix table tells us once more at which position we need to go so we can start again. We then go through the string finding two more matches until we get to S equals S. This is a match, finally, and we increase the I, which is now the same value as the length of the word B. This means we have reached the end of the word, and we have matched the whole word in the text. We now output the position at which this word has been found, which is I positions earlier in the text. At this point, we will want to start searching for the next occurrence of our word in the text. So, as we have already compared the last letter, we use the prefix table to check where we can go back in the string to start comparing again. Turns out it is position 0, so our I gets 0 as value. We then manage to match the first letters of our string, but we then reach the end of the text, and the algorithm ends as j is now equal to the length of the text. Now we have seen how the algorithm works, it is time to think about how efficient it is in terms of the number of computations it makes and the time taken by these computations. The generation of the prefix table runs on a linear time, as it only goes through the word once, and so the time complexity for it is big theta of m, where m is the length of the word. The matching phase is also very efficient because it makes use of the prefix table, which enables it to go through the whole text only once. Therefore, it has a complexity of big theta of n, where n is the length of the text. Here is a table showing how KMP's time complexity compares against the other string matching techniques. In the worst case scenario, the prefix table is full of zeros, meaning it will always return us to the beginning of the string we're trying to match. If this happens, the time complexity resembles the naive method. This is the end of our lecture about string matching. I hope you enjoyed it. Click like and share if you did. We are Paul and Andre, and we approve this message.